Hello, statisticians. Mr. Youngsaber here from Skew the Script. A big question on the mind of college applicants is always, is this college admissions process really fair? Well, today we're going to look at a court case in which a group of Asian American applicants sued Harvard University for discrimination in their admissions process. We're going to look at the case using a chi-squared test for goodness of fit. Let's skew it. Today's lessons on the chi-squared test for goodness of fit. In the fall of 2014, Harvard was sued by a group of Asian American applicants who were rejected in the admissions process. The group claimed racial discrimination. By the summer of 2018, courts overseeing the case decided to publicly release data that Harvard had provided to it about its admissions process. This gave the public an unprecedented view at formerly private admissions data. By 2023, the case made its way all the way to the Supreme Court, where the court found evidence of discrimination. This decision from the Supreme Court overturned the use of race-conscious admissions, also known as affirmative action, at most universities across the United States. So in today's key analysis, we're going to look back at that 2018 publicly released data, and we're going to see if we find evidence in line with the Supreme Court's decision. In other words, according to the data, was there convincing evidence of racial discrimination at Harvard? If you'd like to follow along using our guided notes, you can print them out from our website. So first we'll look at the problem multiple tests and then get into some chi-square stuff. It's new. So we're going to look at data from a secondary report from the plaintiff's statistical expert. The full raw data is unavailable. However, the data we're going to look at today is reconstructed from parts of that report in which the defense and the plaintiffs generally agreed on the findings, so we think it's reliable data. And we're going to look today at academic index ratings. That's an internal measure used by admissions officers at Harvard to gauge the academic qualifications of applicants. So if you're an applicant to Harvard and you have a high standardized test score and high school GPA grades, academic performance, you would get a high academic index rating from Harvard, and that would factor into your application. So we can look at two key distributions here. On the left, you'll see the class of 2019 applicant pool that are in the top 10% of the academic index ratings. These are the top academic applicants to Harvard. And on the right, you'll see the actual admitted class of 2019 from its applicant pool. And you can look at these four groups. These are the four groups that are mainly studied in the plaintiff's report. So those are the ones we're going to look at today and calculate proportions out of. And we can do some comparisons across these groups. So for example, Asian Americans were more highly represented in the pool of top academic applicants to Harvard than they were in the actual admitted class of students. For all other groups, including for white students, there tends to be a bit of overrepresentation, where there's more admitted than would be expected if we're just looking at the top academic applicants. So imagine Harvard claims this: we only accept the top academic applicants and we treat those applicants equally. Our admitted class is as good as a random sample from the pool of top applicants. Is there convincing evidence to refute this claim? Now, Harvard didn't actually claim this exact statement in the court case, but we're going to take a look at it and then do some further analysis from there. So one way to analyze this is we can look at each group individually. Is there a significant difference between Asian American representation in the top applicant pool in terms of academics versus the admitted class? We can look at it for Hispanic, for African American, and for white. But that would lead us to do 4 z-test proportions, and that's a problem. It's known as the problem of multiple tests. We talked about this before. We know that the probability of falsely rejecting a null hypothesis for any test is 0.05, 5% chance of a type 1 error where we get a crazy sample by random chance alone and we falsely reject the null. So I'm going to make a mistake 1 out of 20 times in this way. So if you do many tests and you do it over and over again in many, many tests, you're going to make some errors eventually. And so if we can avoid doing multiple tests, that's best practice. So how can we compare all the groups in just one test rather than 4 tests, 1 for each group? That's where the chi-squared test for goodness of fit comes in. So this is the chi-squared test, and note pronunciation, it's chi, like rye with a K, not a chai latte, not tai chi, it's chi squared. And here are the hypotheses for this test. In this case, The racial distribution of admitted students is the same as the claim distribution. That's the null, where the claim distribution is the racial breakdown of top academic applicants. And the alternative is that the racial distribution of admitted students is not the same as the claim distribution. Note how this follows the innocent until proven guilty framework for null and alternatives. The null is that there's no racial discrimination, so the distribution of the admitted students matches the pool of top academic applicants, the claim distribution. And the alternative is that the distribution of admitted students did not match the pool of top academic applicants, so there might be something else going on there that might lead us to have evidence to prove quote unquote guilty. So let's look at how this fits into the logical hypothesis and what we're about to do. So we always start by assuming the null is true. In this case, we're going to assume Harvard's admissions process is similar to randomly sampling from the distribution of top academic applicants. There's no discrimination. We're just randomly sampling from the top academic pool. Then we're going to compare the distribution in the actual sample of admits to the population of top academic applicants. We're going to assume the null is true. How likely is that data, our actual sample in the class of 2019 that we've gathered? And then we're going to draw a conclusion from that comparison. If it's different enough, if the actually admitted applicants are different enough in their breakdown racially from the top applicant pool, we might reject the null hypothesis and say there's something else going on. So first, let's look at the top academic applicant pool. In total, Harvard admitted 2,023, that's our sample size, applicants from these racial groups into its class of 2019. And here are the proportion among those racial groups in the top academic applicant pool. So we can ask how many from each group would we expect to admit if we're just randomly sampling? If we got 2,023 random draws from this top applicant pool, how many from each racial group would we expect to end up in the class of 2019? Well, we can calculate expected counts by doing this process. So if 57.5% of the top academic pool were Asian, we would do 57.5% of 2,023 random draws from the total pool would be Asian students in our class. That's 0.575 times 2,023 to get 57.5% of that. That's 1,163 students. So we'd expect 1,163 of the admitted students to be Asian American. And we can do that for the rest of the racial groups and come up with an expected counts distribution. So step one, assuming the null is true, here's what we'd expect if we're randomly sampling from the pool of top academic applicants. Now we're going to compare that to the actually observed data in the class of 2019. Here were the students actually admitted to the class of 2019. And then we're going to ask, is the observed data different enough from our expected counts under the null of random sampling from the top pool of applicants? Well, let's look at the differences and add them all up. That's one way we could do that. So we're going to take the observed counts and subtract the expected counts. For the Asian American group, that's negative 731. And for the other groups, we get some positive numbers. So initial thing to notice here is that for the Asian American group, there were fewer admitted than expected, given what we saw in the top academic applicant pool. And for all other groups, including for white students, there were more admitted than expected, given what we saw in the top academic applicant pool. So one way we can kind of gauge the total differences here is add them all up. But unfortunately, when we do that, we get a value of approximately 0 because the negatives cancel out the positives. So one thing we could do is square these. And when we square them, the negatives go away. And so that would help us with adding it up and getting a sense of the total difference because we're squaring away the negatives. But the problem is that we don't really know what these squared values mean. It's hard to interpret what a squared difference really means in terms of our problem. So give me some room for a second. I'm going to go into a little side tangent about donuts, and it's going to relate to what we're going to do in a second. So first, I want to plug Best Donuts. This is a donut shop in Thousand Oaks, California, where I'm from. It's the best donuts in the world. It's as advertised, the best donuts. Please go there if you have time. And we're going to use an example using donuts. So imagine situation one. You order 3 donuts for yourself and 2 friends. But when you get home from the donut shop, there's only 1 donut in the bag. Versus situation 2, you order 600 donuts to pass around school and make yourself popular because you're giving everyone a donut, but there's only 598 donuts in the bag. What difference is greater? Well, let's look at observed minus expected like we did before. So in both cases, there's a difference of 2. We got 2 less donuts than we expected. So the raw difference in terms of number of donuts is exactly the same. However, to get a sense of the differences in scale of what we expected, we can divide by the expected counts. So when we do that, we divide the first situation by 3 and the second situation divided by 600. And then we can get some percentages from that. In situation one, I lost 67% of the donuts that I was expecting, 2 out of 3. In situation two, I only lost 0.3% of the donuts I was expecting. What does this mean practically? Well, in situation one, if I'm expecting 3, I only get 1, then they messed up my order. That wasn't by chance. That was on them. And so I might go in and complain. Now, Best Donuts would never do that. They always get the orders correctly. It's the best donut shop. You should really go there if you're ever there. Now, situation two, it might just be a random chance mistake. I'm only losing 0.3% of the donuts I was expecting. Maybe there's some like production line mishap by chance alone. It happened. So I might not complain. I might not even notice the difference. So to get a sense of these differences in scale of what we expected, we can divide by the expected counts. And that's how our test works. So we're going to divide by the expected counts here, get these numbers, and then we're going to add up all these numbers. This is the sum total of the squared differences scaled by what we expected. This is the chi-squared test statistic. To write this out formulaically, it's just this: the sum of the differences between what we observed by expected squared divided by what we expected. So when this is big, when the sum total of all that is big, that means the observed data is very different from what we expected. Those differences are very large. And so therefore, if the null is true, what we observed is unlikely. We're going to get a low p-value. We're going to reject the null because under the null assumption, our observed data is unlikely. And so we reject the null. When chi-squared is small, when this all adds up to something very small, that means the observed data was very similar to what we expected. That observed minus expected differences in the numerator are very small. We're getting very close to 0 up there. And so therefore, if the null is true under that assumption, your observations were pretty likely because what you got was very close to what you expected. You're going to get a high p-value and you're going to fail to reject the null hypothesis. So is this chi-squared value big enough to reject the null? I'm going to tell you right now, it definitely is. How do I know that? Well, I'm going to show you during our 4-step process here in a second. So let's go through that 4-step process to see what we should show on a real AP Stats free response question. Remember, the 4 steps for inferences are a way to show your work. You might get a question like this: here's what we've been analyzing this whole time. And then they ask you to provide convincing evidence. In that case, we're going to do the 4-step for inference, and we're going to use our hypothesis test. First, state the hypotheses and the significance level. We state our null and our alternative, which we wrote out before, and our significance level is 0.05. Plan: we're going to name the inference method and check conditions. We're going to conduct a chi-squared test for goodness of fit. Here are the conditions. These conditions are a little bit new. Some are similar to before. Random. We're assuming that the admitted students were randomly sampled from the pool of top academic applicants. So we're going to assume that random condition is met because that was what we're testing. Next, let's check the 10% condition. The sample size should be less than or equal to 1/10 of the population size. So in our case, 2023, which was the number of admitted students, has to be less than or equal to 10% of all top applicants to Harvard, which is the population that we're sampling those 2023 students from. Now note that in this case, 2023 may not actually be less than 10% of all top applicants to Harvard. So we're going to proceed with caution. I would go ahead and write that on the AP exam. And note that on AP exam free response questions, if you're unsure if a condition is met, write that you're unsure and also write proceed with caution and conduct the test anyway. You don't want to put yourself in a situation where you lose points for not conducting a test that you should have conducted. And then finally, the large counts condition. In this case, for chi-squared, all expected counts have to be greater than or equal to 5. We calculated the expected counts before. We should show that on our paper and show that they're all greater than or equal to 5. Now, for the do phase, compute the expected values, degrees of freedom, test statistic, and our p-value. So the expected counts we got before, so we're just going to write that down because we got those up by hand. We'll show our calculations. Degrees of freedom, in this case, degrees of freedom for chi-squared is going to be the number of groups that we're studying minus 1. In this case, we have 4 racial ethnic groups. So we're going to do 4 minus 1, that's 3. So we have degrees of freedom there. The test statistic, that's the chi-squared that we calculated before. And here's the formula. What we can do to lessen our time on the FRQ is show a couple of these. So we can do the observed minus the expected squared divided by the expected for a couple of groups, add them together, and then do a plus ... a little ellipses. So we don't have to write it all out. And then we can use our calculator to get this value for us. That's actually preferred, I think, because you're likely to make a mistake if you do it all by hand. The way to do the calculator, the instructions are right here. Take a pause in the video if you want to try it on your own TI-84, and then we'll come back. So when you do that in the calculator, it will spit out your chi-squared test statistic, which is what we got before, 3,860. And the p-value I had was about 0. It's so small that it's close to 0 in the calculator. So finally, we conclude, well, because our p-value of about 0 is lower than our alpha value of 0.05, we're going to reject the null hypothesis. We have convincing evidence that the racial distribution of admitted students is different than that of the top academic applicants. We have convincing evidence of the alternative. So now let's discuss this result. We found convincing evidence that the racial distribution of admitted applicants is different than that of the top academic applicants. And specifically, Asians tend to be admitted at lower rates than what we expected. All other groups studied, including white applicants, were admitted above the expected count. And also, what this plaintiff study found was that Asian applicants tended to receive better extracurricular weightings as well on average compared to the other racial groups studied. So the evidence we have so far is that Asians tend to be admitted at lower rates than expected if we base that expectation solely on their academic ratings. And then Asian applicants tend to be get better extracurricular ratings from Harvard on average compared to other racial groups. So imagine that you're at the Supreme Court and the plaintiffs argue that this evidence we've seen so far proves racial discrimination. Now, imagine that you're in the shoes of Harvard's lawyer and had to defend the university. How might you have attempted to defend the school's admissions policy? Explain your thinking, and then we'll discuss that in class. That's it for today's statisticians. We'll see you next time.